Good evening, everyone, and welcome to the Amateur Radio General Class, session number 19. During our previous session, we had our usual question pool review. We also looked at what the voltmeter, the two types are analog and digital. We also discussed other pieces of test instruments and tools, the oscilloscope, antenna analyzer, directional wattmeter, and the field strength meter. We also looked at what the two-tone test was. We also looked at the bypass capacitor, ferrite choke, what grounding and bounding are, RF voltages and RF burns. We also discussed electrical noise, what the DSP IF filter, as well as the speech processor and the S meter are. When we look at our curriculum, we see that we are progressing very nicely. We expect to wrap up the amateur radio practices topic today and also commence operating procedures. Again, an encouragement to persons to consider taking the practice exams. And we had no outstanding questions from the last session. So we go straight into our question pool review. So for persons who are following along with the PDF copy of the No Nonsense General Class License Study Guide, we are on page number 61. So let's go straight into the questions in the question pool. The first one, what is an advantage of a digital voltmeter as opposed to an analog voltmeter? We said that the digital voltmeter gives us better precision for most uses. Next question in the question pool. Why is high input impedance desirable for a voltmeter? So we discussed the reason for this the last session. We said that when we put the voltmeter into the circuit, we don't want it to affect the circuit too much, but we want to get a reading. So that's why a desire is to have a high input impedance, so it doesn't draw much current to take the reading. So the reason is it decreases the loading on circuits being measured. Next question in the question pool. What is an insurance in which the use of an instrument, I say again, what is an instance in which the use of an instrument with analog readout may be preferred over an instrument with digital readout? So let's dissect this question a little bit. What are they asking us? What is an instance? Meaning when? Will using an analog meter be preferred to one that's digital? So remember, we had given some nice advantages of the digital meter, like in the question before, higher input impedance and so on. But under what conditions or in which instance will an analog actually be preferred over digital? And we had said that instance for us as amateur radio operators is when we are adjusting tuned circuits. That's when that analog display will come in very high, very, very nicely. Okay, continuing in the question pool. Next question. What item of test equipment contains horizontal and vertical channel amplifiers? Okay, let's dissect this question a little bit. What are they asking us? They're asking us for the name of the test equipment. But what type? Or what's the property of that test equipment? Or what does it have? They say it contains horizontal and vertical channel amplifiers. So when we had discussed the oscilloscope, we saw that you had a vertical input and a horizontal input, and you have a graph as a result of those two inputs. And of course, we said the inputs have amplifiers to amplify the signal and show it on screen. So that's the item that they're referring to, that piece of test equipment known as an oscilloscope. Moving right along. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? Okay, fair enough. What's an advantage of an oscilloscope? That's what they're asking us, compared to your regular digital voltmeter. We learned that you have a very nice graphical display, x-axis, y-axis, and you can see some complex waveforms as well as you can measure them. So that's the answer. Complex waveforms can be measured using an oscilloscope. Remember, the digital voltmeter just gives you values and digits. But your oscilloscope, you can display what a waveform looks like, and you can also get measurements. Okay, yet another question. Which of the following is the best instrument to use when checking the keying waveform of a CW transmitter? Let's dissect this question a little bit. What are they asking us? So they're asking us for the best instrument. But to do what? We are checking keying waveform of a CW transmitter. Remember, we said CW is continuous wave, but it's associated with Morse code. So in other words, when you're doing Morse code, what instrument is the best one to check that keying waveform? Remember, we showed a graph when you are keying and using Morse code, how we have the rise and then the fall. And you want to see that to make sure it's a nice waveform for CW. Well, the best instrument is our trusty oscilloscope. Right, moving right along. Next question in the question pool. What signal source is connected to the vertical input of an oscilloscope when checking the RF or radio frequency envelope pattern of a transmitted signal? Let's dissect this question a little bit. So they're asking us for the signal source connected to the vertical input. So in other words, what do we plug into the vertical input of an oscilloscope? Remember, we have the vertical input, we have the horizontal input. Well, which one do we plug into the vertical input when we are measuring the RF envelope pattern of a transmission? So we're having a transmission and we want to look at the RF envelope pattern. What do we stick into the vertical input of that scope? And the answer we saw is we use an attenuated RF output of the transmitter. Why attenuated? Remember, we said attenuation or attenuate. When you hear attenuated, we mean reduction. The RF output from your transmitter is a very strong signal, and your oscilloscope could be damaged if you were to transmit straight into the oscilloscope. So you have to attenuate it. So that's why the answer is the attenuated RF output of the transmitter. You have to put an attenuator or a sampler to just take a small portion of the signal and send it to the oscilloscope so that you don't damage it. So that's the answer, attenuated RF output of the transmitter. Next question in the question pool, and I take this opportunity to remind students that the number in brackets right after, or the couple of characters right after in brackets, each question is the question pool number. So the full question pool with the full question and all of the answers, or rather the correct answer plus the distractors A, B, C, D, were circulated, but we don't go through all of them because that'll take an enormous amount of time for us, and you can check that on your own. But if you want to find the relevant question in the question pool associated with this and see what the distractors, the wrong answers are, you can just search for this, Control F on the PDF and type in or copy and paste G4B11, or in phonetics, Golf 4 Bravo 11 in your PDF finder, and it will take you straight to that question in the question pool, and you'll see all of the choices A, B, C, and D, and you will be able to see what the wrong or the distractors are just for your reference. So, continuing. Which of the following must be connected to an antenna analyzer when it is being used for SWR measurements? Let's dissect this question a little bit. What are they asking us? What do you connect to an antenna analyzer? Not a voltmeter, not an oscilloscope, not, right? It's an antenna analyzer that we're talking about. But what type of measurements are we taking? We are doing SWR, or standing wave ratio measurements. Well, the antenna analyzer, and it's analyzing our antenna, and we have to connect the antenna to the analyzer with something, the feed line. So that's the answer. The antenna itself, as well as the feed line that you connect between the antenna and the analyzer. So that's what you connect when you are doing SWR measurements using an antenna analyzer. You connect the antenna and the feed line. Okay, moving right along. What is a use for an antenna analyzer other than measuring the SWR of an antenna system? Let's dissect this question. They're asking us about an antenna analyzer. We just had a question on an antenna analyzer, but they're asking us, other than measuring SWR, what other use can you use it for? So we found out during our theory session last time, we can also use the antenna analyzer to determine the impedance of the coaxial cable or the feed line. So that's what the antenna analyzer could also be used to determine. Impedance of coaxial cable. Next question. What problem can occur when making measurements on an antenna system with an antenna analyzer? What problem can you have? What can you encounter? What can cause probably an incorrect value? Well, we had said with an antenna analyzer, remember we said it contained a little transmitter. It sends a signal to the antenna, and then of course it measures the reflected power coming back and will give you the SWR and so on. Well, because it's a transmitter and a receiver, strong signals from nearby transmitters can affect the accuracy of measurements. So if you have a strong transmitter either at your location or your neighbor or very nearby, that antenna analyzer could pick up that strong transmission and you'll get an incorrect reading. It will probably have too much reflected power, and therefore you find your SWR is high, or some other inaccuracy that you get. So you have to be careful when using antenna analyzers about strong signals that are nearby. Continuing. Which of the following can be determined with a directional wattmeter? So the instrument that we are talking about now is the directional wattmeter, not the oscilloscope, not the antenna analyzer. But what can we determine with that instrument called the directional wattmeter? We can determine SWR, standing wave ratio. Remember we said we transmit and have it look at the forward power, then we switch to the reflected or the reverse power, and then we can plug that into a trusty formula, and we'll get SWR. So that's what we can get from our directional wattmeter. You can also get a direct readout of the SWR, as we said earlier, from your antenna analyzer. So with the directional wattmeter, you have to do a little bit of work, but guess what? You can still get SWR using your directional wattmeter. Next question in the question pool. Which of the following instruments may be used to monitor relative RF output when making antenna and transmitter adjustments? Okay, so we are monitoring relative RF output. In other words, some kind of signal strength when we are doing antenna and transmitter adjustments. Remember we showed a little instrument that we could walk around or move the antenna around, and we can see what signal strength it is, and we could even plot it on a graph. Plotted on a graph. Well, that instrument, we had called that a field strength meter. Moving right along. Which of the following can be determined with a field strength meter? Well, we alluded to it just now. We can plot the radiation pattern of an antenna using the field strength meter. Remember we showed we had an antenna with a transmitter, and then we can have this trusty field strength meter in our hand. We can move around and we can measure the strength of that signal, and then as we walk all the way around the antenna, all 360 degrees, we can plot that on a graph, and we can then determine the radiation pattern of the antenna. Maybe there are some lobes, a forward lobe, maybe it's a very directional antenna, and you can see the forward lobe, and maybe you can see the front to back ratio, you can see low signal off to the sides or to the back. Next question. What type of transmitter performance does a two-tone test analyze? So we said the two-tone test is to determine the linearity of your transmitter. Next question. What signals are used to conduct a two-tone test? So we said there's a property of those two tones. Remember we showed there some software we can use, there are devices you can also use to generate those two tones. You can choose what those two tones are. But in choosing those two tones, we said that those two tones must be non-harmonically related audio signals. So they're audio signals, yes, but one must not be a harmonic of the other. So that's what's meant by non-harmonically related. Okay, continuing. What sound is heard from an audio device or telephone if there's interference from a nearby single sideband or SSB phone transmitter? Let's dissect this question a little bit. So first of all, they're talking about interference, meaning that your amateur radio station is causing interference maybe to home by you or a neighbor, and you are using SSB or single sideband, and you are doing a phone transmission. Remember, we said phone when we talk about phone in amateur radio, we mean voice. So you're using single sideband voice. But what sound can you hear in an audio device or telephone? Meaning you're causing interference to someone. What are they likely to hear? They are likely to hear your distorted speech. That's how you know you're causing interference with SSB. Next question again, similar line. What is the effect on an audio device when there is interference from a nearby CW transmitter? Let's dissect this question. They're asking us, okay, we are causing interference. As an amateur, we are transmitting, we are causing interference to some audio device. But we are using CW. And remember we said CW is continuous wave, but it's associated with Morse code. So when you're transmitting Morse code, what does that audio device interference sound like? How does it sound? It sounds like an on and off humming or clicking sound. Next question. So now we come to doing something about the interference. Which of the following might be useful in reducing RF or radio frequency interference to audio frequency devices? So we're causing interference. Earlier we said we had SSB causing interference, CW causing interference. But what can we do to those audio devices? We said, and this is where learning the various types of components. We talked about resistors, capacitors, inductors, and so on. So this is where learning the properties of these components come in. We can use them to solve problems, and that's exactly what we do here to reduce the RF interference to audio devices. We can use a bypass capacitor. Okay, yet another question. Which of the following would reduce RF or radio frequency interference caused by common mode current on an audio cable? So we said that, sometimes our transmitter, the stray RF, could get onto the audio cable and cause interference. And we also talked about this before, sometime earlier in our general class, which is the ferrite choke. So we said if you place a ferrite choke around the cable, that can reduce such interference. So you see, we have techniques to solve problems of interference. Moving right along. How can a ground loop be avoided? So remember I said ground loops are not good. We need to avoid them. So you can avoid a ground loop by connecting all ground conductors to a single point. Instead of sending each item to a ground, you connect all to a single point. Next question. What could a symptom of ground loop somewhere in your station? Say again, what could be a symptom of a ground loop somewhere in your station? What's the symptom when you have a ground loop? Well, you receive reports of hum on your station's transmitted signal. What that means is that another amateur radio operator that you're talking to, for instance, will tell you you are sounding as though you have a hum in your transmission. That's what they mean. And therefore, it could mean that you have a ground loop that you need to solve. Continuing. What effect can be caused by a resonant ground connection? So we said if you have a ground to your station and it is resonant, what you can end up having is high RF voltages on the enclosure of your station equipment. Because remember we said now, because your ground connection is resonant, you are transmitting on your ground And because you're transmitting on your ground to your chassis of your equipment, your radio, your tuner, all your pieces of amateur radio equipment, it's grounded, yes, but that ground connection is resonant. It's operating like an antenna. That's what that means. You can have, remember we said RF or radio frequency involves voltage, current, and of course it's an electromagnetic wave. So there's electro, meaning current and voltage. So if your ground connection that is supposed to be a ground is resonant, you can end up with high RF voltages on the enclosure of your station equipment. Not good. Next question. What might be the problem if you receive an RF burn when touching your equipment while transmitting on an HF or high frequency band, assuming the equipment is connected to a ground rod? Right, so again, similar theme. You get an RF burn, not nice, when you touch your transmitter. All right, but you're grounded, huh? What could be the problem? Well, we said that it could be that the ground wire has a high impedance on that frequency. With that high impedance, it ends up sounding as an antenna, really. And, you know, that's when you're going to get your RF burn if you touch the transmitter. So that's a grounding problem, right? It causes, or the ground wire has a high impedance. Not good. Your ground should have a very low impedance. Okay, and just bear in mind that direct current impedance is one thing. Alternating current or radio frequency impedance as frequency increases could be something else. So bear that in mind. All right. What must be, say again, why must the metal enclosure of every item of station equipment be grounded? Why must you ground every single piece of equipment? Well, again, it solves what we talked about a bit earlier too. It ensures that hazardous voltages cannot appear on the chassis or the body of the equipment. That's why you make sure you need to ground every single item in your station. Next question. What technique helps to minimize RF or radio frequency hotspots in an amateur radio station? So we had talked about bonding the last time, the importance of bonding all your equipment together. That's why you do it, to avoid your RF hotspots. You don't want to touch it and then you get an RF burn or a zap. So you bond all equipment enclosures together. Let's continue with questions in the question pool. Which of the following could be a cause of interference covering a wide range of frequencies? So let's dissect this question. They're asking us about interference and the cause of the interference, but what is the nature of the interference that we're getting? We're getting a wide range of frequencies you're getting interference on. So we said that anytime you get an interference across a wide range, probably whole spectrum or several bands, chances are that is caused by arcing at a poor electrical connection. It could be in your home, it could be outside on the pole, it could be very close by. That arcing will cause wideband noise. Moving along, which of the following is an advantage of a receiver's DSP IF filter as compared to an analog filter? Let's dissect this question. So they're asking us about an advantage of one thing over the other, but what are those two things? A receiver's DSP IF filter, digital signal processing intermediate frequency filter. What's the difference between a digital compared to an analog filter? So we said that the DSP has a very nice advantage where a wide range of filter bandwidth and shapes can be created because it's digital, it's done in software. Okay, let's see if we can quickly finish up some of these questions before we take a break and then go into our theory this evening. What is the purpose of a speech processor as used in a modern transceiver? We said that it increases the intelligibility or understandability or readability of transmitted phone signals during poor conditions. So that's the advantage of a speech processor or the purpose of it. Which of the following describes how a speech processor affects a transmitted single sideband phone signal? So we showed a diagram of unprocessed speech and we had showed what the processed speech looks like, and that processed speech shows an increase in the average power. So that's what causes our signal to go a little further, because the average power of a transmission is stronger by having processed or compressed our speech. So the answer is it increases average power. Next one. Which of the following can be the result of an incorrectly adjusted speech processor? So like every good thing, it could come to naught if it's not properly used. So if we don't use our speech processor properly, or we don't adjust it properly, all of the following can occur. We can have distorted speech, sound really bad. We can have splatter, meaning we can transmit on frequencies unintended. And then of course we can have excessive background pickup. You're hearing all sorts of things in the background that you really don't want. You just want your voice, the relative information, the relevant information to be heard, but all sorts of background noise is being picked up, and people are hearing that instead of your voice, or overriding your voice, or with your voice. Next question. Short and sweet. Where is an S meter found? So we showed what an S meter is. Nice gauge that shows this received signal. Therefore, it is found in a receiver. What does an S meter measure? Well, we said it is signal strength in a receiver, so therefore it measures the received signal strength. How much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9? Let's dissect this question a little bit. So what they're asking us, I'm at a receiver and I'm receiving a person at S8, signal 8, S8, that's what I'm seeing. But they want to know by how much must the power output of the transmitter, the person that is communicating with me, how much more power, or what order of power do they need to raise it by for me to see their signal go up from S8 to S9, right? And it's like a driving at 80 kilometers 80 kilometers per hour, and how much more power you need to apply to your engine for it to go to 100 kilometers per hour. That's basically what they're asking us, that type of thing. How much more power the transmitter needs to put out so that we see that needle go from S8 to S9. So we said that it's 4 times increase. So for any further detail, just review the the theory from last session, or the slides in the slide deck, where we gave a full explanation of that. Also, a similar question: how does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S meter? Okay, so let's dissect this question. So what they're asking us is, you have an S9 signal. You're seeing that on the S meter. And there's another signal that says that is 20 dB or plus 20 dB over S9. They want to know by how much times must that power be for it to increase from S9 to go to 20 over S9. And we showed that the answer to that is 100 times stronger. So again, we worked through that in quite a bit of detail during our previous session, and I encourage you to review that if there's any doubt as to how we get 100. So folks, at this time, let us take a short 2-minute break. Get up, take a stretch, have a bathroom break, probably have a drink of water, and we'll come right back and we'll pick up in the we'll pick up in the slides, in the slide deck. We'll go into some theory. Okay, everyone, welcome back. So let's go straight into our theory for today's session. So we want to discuss now the concept of band edge and frequency range. So we had discussed this already in the technician class, and we also touched on it again during our general class. And as amateur radio operators, we have to make sure that we operate properly. And one of the concepts we need to be aware of is when we're using our frequencies, that we do not go outside of the permitted frequency range that we have, that's according to the license and the license class that we have. We have to make sure we stay within it. And we need to be aware that our frequency, when we use it, doesn't occupy a spot on this frequency spectrum. It occupies a bandwidth or an amount of spectrum to the left or to the right of that center frequency. So whatever dial that we have on our radio, whatever frequency we put into it, let's say 7.718178, for example, we need to know where else, apart from that center frequency or that frequency that we put in, where does it occupy? And I'll be using the concept of a car on a roadway and being in a lane to show and illustrate the concept that we need to stay in our lane. And therefore, as an amateur radio operator, we also need to stay within the frequency range and do not go outside of the band edges. So on an amateur radio license, it will specify your frequency range or permissible frequency range depending on your class of license. And you need to be aware of it. And also you have bands and sub-bands as well. So if we remember, when we were talking about single sideband, remember I said we have the center frequency, and even though our radio will have that frequency on the display, we need to know if we're doing lower sideband, it occupies some spectrum just lower than that center display. And if we're doing upper sideband, we need to know that the signal will occupy some spectrum above the center frequency. So we need to know how much we're occupying. So for instance, with an SSB signal, we may be occupying 3 kilohertz wide. So if it's 3 kilohertz wide, we need to make sure that we are not crossing the band edge or the edge of the frequency band that we are using. So we need to be deterministic about that as amateur radio operators. So we say that both a lower sideband and an upper sideband signal will occupy, let's say, 3 kilohertz, but the lower sideband will occupy 3 kilohertz below the center frequency or the displayed frequency. But an upper sideband signal will occupy, let's say, 3 kilohertz above the center frequency. And when you're using that 3 kilohertz, let's say using lower sideband, and you're doing voice, you're speaking, you need to make sure that that center frequency that you have displayed is at least 3 kilohertz above the lower edge. Because if it's not at least that, when you transmit, you may go beyond the edge of the band. So the example that we have here, and it's a question in the question pool, is if you have your carrier frequency set to 7.178, if that is your center frequency, or that's what your carrier frequency or the display frequency on your radio says, and you're using lower sideband or LSB, that means you're going to be transmitting all the way to 3 kilohertz below 7.178. So your transmission will actually occupy from 7.175 to 7.178. So your carrier frequency or your radio display is 7.178. But you are transmitting with a bandwidth of 3 kilohertz. So you have to subtract 3 kilohertz from 7.178. And that's how we get the 7.175. We subtract 3 from the 8 and we get 5. So this frequency range is what your transmission will actually occupy. And you need to make sure that you're within your range, your band edge, or your subsegment. Similarly, if we are doing upper sideband transmission and you're using voice, you need to make sure that you are at least 3 kilohertz below the upper edge. So the example that we give, let's say you're on the 20 meter band, your frequency, you plug into your radio, you dial up 14.347. But when you transmit, because you're transmitting upper sideband, and that signal is going to take up 3 kilohertz, your transmission is actually occupying 14.347, which is what your readout on your radio is saying. But it also goes all the way up to 14.350. Your signal occupies all of that because your transmission occupies bandwidth. And that range is where your signal will be. And if you don't take that into account, you might actually transmit above the band edge. So the idea is not to go at the band edge, stay a bit away from the band edge so that you don't cross it at any point in time. So that's, for example, I use the cars in the lane example. If we have a car here, we want to drive in the lane. We don't want to be in the middle. We don't want to be at the edge on the grass or whatever it is. So this is incorrect. This is correct. You have to be in your lane. It's the same thing when you are transmitting. You need to transmit within the band that you're licensed for, whether it's upper sideband or lower sideband. If it's upper, you can't be outside of your lane. You have to stay in your lane. So let's discuss now mobile operations and power supply. So mobile operation, for instance, you're operating out of your car. We need to be aware that when we have our radio, so this is our radio, and our radio may comprise of different components as well. Notice you have the chassis of the radio, you may have a different control head, you have a microphone, you may even have a tuner, and you have your antenna and so on in your car. But you have to power your equipment somehow. And typically in your mobile, you will connect it to the car battery. So we have our firewall, and inside of your engine compartment, usually you have your battery and you have wire that goes from your battery to your radio or your transceiver. But we need to know, for instance, let's say this is a 100-watt HF mobile radio. You need to make sure, because it's 100 watt, it's drawing a fair amount of power from your battery. You need to use heavy gauge wire. You cannot use a thin gauge of wire because of the amount of power draw. So on that fused connection that you have directly to your battery, for your exam, you need to know that it's going to be heavy gauge wire that you use for that directly fused power connection to your radio. Also, this diagram at the bottom, or this picture at the bottom, should look familiar to many of us. It's a picture of what we typically call a cigarette lighter adapter. Formerly, it's called the auxiliary power socket, because sometimes it's no longer a cigarette lighter inside of there. So we call it an auxiliary power socket, but some of us may know it as a cigarette lighter adapter because some of those cars still will come with that cigarette lighter adapter. You push it in, it'll get very hot, red, and you know that's what persons would be using to light cigarettes back in the day, maybe still so. But we're saying that you can power a radio using that socket, that outlet, to get 13.8 volts DC. But we're recommending, in the case of an HF radio in your car that is running 100 watts, you don't want to use that connector at all because the wiring inside of there may not be adequate for the amount of current that your radio will draw. So the idea is, an amateur radio world, when you put in your high power radio inside of there, you will not want to and should not be using that accessory connector, what we call the cigarette lighter adapter, for that HF radio. If you're using it at all, it should be for some very low powered equipment. But your 100 watt HF transceiver, if you put that into your radio and plug that in, you'll probably melt the connector, you might melt the wires, you might trip the fuse, but you should not be using it. And you need to know that for the exam, it is best not to use that connector for your 100 watt HF transceiver because the wiring may be inadequate. The gauge of wire might be too thin for the current that is being drawn by your radio. Like everything else in amateur radio, we can sometimes cause interference or we can receive interference, and that's why we are trained as radio operators. We know how to avoid causing a harmful interference, and we know how to avoid receiving interference. But guess what? When we go into our mobile operation, we can also receive interference from that same car, that same van, that same vehicle that we are installing our amateur radio inside of. There are electronics inside of there that can cause us stress and heartache. But guess what? No stress. Why? Because we are licensed amateur radio operators and we know what are some of these things, and we even have some of the remedies towards it. So we need to first, of course, to have a problem, you need to recognize you have a problem, and we need to know what can cause us to have these problems of interference in our mobile vehicle. So we say that a radio installed in a vehicle is susceptible to noise from the electronics inside of the vehicle. You may receive interference, buzzing, humming, snap, crackle, pops. different types of things may occur when you are listening to your radio because of these electronics. What are these electronics that we're talking about? And for your exam, you need to know this. The battery charging system. Yes, you may have an alternator that's charging your battery, and you may have some alternator wine and so on coming from it, or whatever circuit that's charging your battery. You may get some noise associated with that. That's the first system. And we have some little pictures here that shows these subsystems in your car that can cause, those electronic subsystems that can cause that bit of interference. The fuel delivery system as well has some electronics, and those things firing and the injectors firing and so on can cause a bit of interference as well on your transceiver. You may hear some noise. And also your vehicle control computer. Yes, most computers today, nowadays, whether it's electric vehicles or electronic ignition, you have computer control. These things are monitoring all sorts of temperatures, pressures, and you try to optimize your vehicle's efficiency. So that control computer, what you call a brain box, some people know it as, that operation with all of the circuits can cause interference on your HF radio, or your radio inside of your car when you go mobile as an amateur radio operator. So when we go mobile as well, we need to use an antenna. So on the right hand side here, we have a base station antenna. It's very tall. This is what, probably a 21-foot length antenna. It's installed outside of a house or a building and so on. And that's for HF. Remember, for HF, we said we have very long antennas because the wavelength is very long for HF frequencies, several meters in length, okay? But when we go mobile, we cannot, or we should not, and in some cases it's illegal to put such an antenna structure on a vehicle. So we have to use something that's much smaller. When we do that, for the same frequency, we are really compromising, and that is a major limitation. Let's say we're doing HF operations inside of our car. We cannot put up the long wavelength type antenna with traps and all of that. We have to use a compromised antenna, and that's a main limitation of an antenna system that's used for HF in a vehicle. The other disadvantage that we have is the fact that because we are using a shorter antenna like this one, last time we showed a coil antenna, it's shorter, yes, it will be resonant, it will work, you know, you'll have a good SWR, reasonable SWR, and you can transmit. But because it's not a full-size antenna, you may find that the operating bandwidth might be very limited. So you may have to tune and tune regularly and so on, compared to a base station antenna where the bandwidth might be a little better. It might be a low SWR across a range of frequencies more so, but with the mobile antenna, you might have to tune. And if you are lucky enough to have a tar heel type antenna or coil antenna like this, and you can tune up and down, that'll be great. But if not, you might very well find that you have high SWR north or south of the frequency that it is resonant on. So you have a very limited operating bandwidth. If you go up a little bit on the frequency, you go down a little bit on the frequency, you might find that your SWR is high. So that's another little disadvantage that you have